All right, let's get started. Brennan, I have past presenting and host privileges to you. So please feel free to.
Yeah, let's see. If it's
I
okay,
think
I'm
David will
gonna
be our
try
first.
and the first one
Okay,
here.
cool.
Let's see it. All right. So I'm sharing my screen right now, and everyone can hear me okay. All right. Hi, my name is David, and I will be starting off this presentation on. So our presentation is going to be on frequency curves and hydraulics primer, and I'll start off the presentation talking about frequency curves. This will be a general discussion on developing frequency curves and when to use different types. So developing frequency curves can be a pretty detailed and sometimes complicated process. So in this presentation, I'm just going to try and provide a high-level overview. We do have classes here at HEC that specifically talk about developing frequency curves. So if you wanted to learn more and go into more detail, I highly recommend taking that class. Also, I want to credit a lot of my slides I stole from Richard. So all the cool slides that you see, you can thank Richard for that. All right, so frequency curves is one of our main inputs into the FDA model. Here, I'm just showing you the classic 4-curve diagram that describes the FDA process. So the top right is our flood frequency curve. The top left is the flow stage curve. Bottom left is the damage stage curve. And then lastly, we have the damage frequency curve that we use to estimate the expected annual damages. So you'll be seeing this curve a couple times throughout our presentation. And so what I'll be talking about is that first curve there that we have highlighted. The first topic we'll cover is analytical and graphical frequency curves. So before that, right, what is a frequency curve and what does it tell us? So a frequency curve is a visual representation of the distribution of your data set. And what it tells us is the probability for a given flow. So using this kind of graph I have here on our right, let's say we wanted to know what the 10% annual exceedance probability is. So to that, we look for that 0.1. Right, so this 0.1 is 10 over 100, right? That gives us 10%. So we just move straight up from the 0.1, and then we go over to the left, and we see that for the 0.1, this curve shows us that it's about 100 CFS. So the 0.1 annual exceedance probability is 100 CFS. So this image we're showing is some of the typical outputs that we might see from an analytical flow frequency curve. We know that it's a flow because of the y-axis. It says flow there. The red line is the computed curve. The dashed green lines are the confidence limits that reflect that uncertainty around the red curve. And then we have this box to the bottom right here. These are the statistics or the moments that were used to compute the analytical curve. And then I generated this curve from our HEC SSP software. SSP stands for Statistical Software Package. And one of the main purposes of this package, of this software, is to compute frequency curves. So if you were to get a frequency curve, an analytical curve from an engineer, it most likely came from our SSP software. All right, so let's start with analytical curves and how a hydrologist would generally start with creating an analytical curve. First thing we do is get discharge values from a flow gauge. And the top chart there is just showing a flow time series that we would get from a flow gauge. So flow gauges, these are maintained by some government agency. We typically use USGS. And ideally, we want to have more years of record, right? So the more years that we have, the more confident we can be in our flow frequency curve that we generate. Next thing we do is we extract all the peak flows for every year. And what we're doing is we're filtering the data so that we're only doing the analysis on the largest flows every year. We also call this the annual maximum values. So we take these annual maximum values and then we follow a methodology called Bulletin 17C. So Bulletin 17C, this just tells engineers, how you would go about creating a analytical flow frequency curve. The Bulletin 17C, it recommends using something called a log Pearson type 3 distribution. And so log Pearson type 3, you need to have mean, standard deviation, and skew in order for you to generate your analytical curve. So don't worry too much about what a log Pearson type 3 distribution is, but just know that you just need to calculate statistics using for an analytical curve. So to create a graphical curve, we start in the same way where we need a flow gauge, and we are extracting the annual maximum values again. The difference here is instead of doing statistics on it, what we're going to do is we're going to order it. We're going to order those flow values, and then we're going to plot it on a graph. So once we plot it on the graph, we draw a line, and now that line is now our frequency curve. We also call graphical curves non-parametric, since we aren't using any parameters or statistics like the mean or standard deviation in order to create this curve. Here, we're just summarizing kind of what we just talked about with the analytical. We use a log Pearson type 3 distribution, which uses the mean, standard deviation, and skew to compute this analytical curve. So the outputs from this analytical curve, which is the inputs that go into FDA, would be the statistics, which is the mean, standard deviation, and skew, as well as the equivalent record length. So equivalent record length, this typically means your period of record. So how long was the gauge data set that you had used to generate this curve? So graphical. So with a graphical, again, we're also taking annual maximum values. We order it from smallest to largest, and we plot it on a graph, then draw a line. So the outputs for the graphical, and then the inputs into FDA would be quantile flows. So quantiles meaning, for a given, probability, what is that flow? So in our example, we had the 10% annual exceedance probability. That flow value was 100 CFS. Another quantile would be the 1% annual exceedance probability, and then the flow value could be something like 1,000 CFS, right? So you have to specify those relationships into FDA. And then at the same time, we're also going to put in the equivalent record length as well. And that's also going to be something like the period of record. Right, so when would you use one or the other? So I have a number of kind of points listed here, but kind of the main things are use an analytical curve if the stream flow data is unregulated. So that means that flow is not hindered by something man-made. Use a graphical method if the stream flow is regulated, right? And so that just means that flows are being affected by some type of structure. So an example of something that might be regulated is flows that are recorded downstream of a reservoir. Right? So the reservoir is holding back flow and controlling the release of the flow. Right? And so what is being measured by the gauge, right, is based off of what the reservoir is releasing. So that's a regulated stream flow. Another possible reason for using a graphical method is if the analytical curve doesn't fit well against the data. So you can have a situation where the unregulated data, you compute the analytical curve, but then the data, when you plot it against the data, it just doesn't look right. Right? This could be pretty typical in dry areas where you can get zero flows for most of the year. And so those situations, maybe a graphical would work better. So if you are in a regulated situation, which happens pretty often in major streams, you could unregulate the flows, then perform an analytical frequency curve. So in hydrologic analysis, we do this pretty often to incorporate more years of record into our frequency curve. So for flow gauges downstream of a reservoir, within the period of record, we'll notice a pretty significant change in your flow magnitudes before and after that reservoir was put in place. So what a hydrologist can do is pretend that that reservoir did not exist by doing computer simulations to see what the flows might have looked like had that reservoir not been put in place. And so that's what we mean by unregulating the flows. And that's how hydrologists, they typically make the big bucks. So why kind of go through that trouble of unregulating a data set? Right, so there are a couple of advantages to using an analytical curve, and I've listed 4 reasons here. The first is it's repeatable. So an analytical curve, it's going to be based off of the statistics of the data set, right? So the mean, standard deviation, and skew. So as long as you have those statistics, right, anybody can recreate your curve. With a graphical curve, if you are drawing it, right, there's going to be subjectivity involved in it. So another person can draw a curve differently than another person with the same data. Second reason, analytical curves, there's a better reflection of the uncertainty around the curve. And that's because Bulletin 17C, it has a process for characterizing the uncertainty. So with graphical, you can also create uncertainty curves, but there's a bit more limitations to kind of what that uncertainty means compared to an analytical curve. Third reason here I've listed is extrapolation. So with an analytical curve, if you have the statistics and you compute the curve, you'll have a curve that can basically tell you the probability, as far out as you want. Of course, you want to be careful to how you use your extrapolation, especially if your data set is limited, meaning you don't have a lot of years of record. But that's part of what we do for. That's one of the purposes of a flow frequency curve, right? It's to tell us what is this flow, what is this probability for this given flow. And then lastly, another advantage for analytical curves is it can allow you to use historic information. So Bulletin 17C, again, we can thank this methodology. It allows you to add information such as paleo floods in order for you to refine your frequency curves. So graphical curves, it's not really clear how you would incorporate historic information. And again, there probably would be a lot of subjectivity to it if it was done. All right, so now we talked about analytical and graphical frequency curves and the differences and when to use one or the other. We'll move on to discussing unregulated and regulated transform functions. So just a reminder, unregulated means data that has been impacted by a structure, and then regulated means data that has not been impacted or altered by a structure. We just talked about one way of creating a regulated curve, which is just to do a graphical flow frequency curve, which again is just drawing the curve. But then we had brought up some limitations about that, right? Namely that it's not repeatable, doesn't necessarily reflect uncertainty that well, challenges with extrapolating and incorporating historic information. So a transform relationship can let you utilize the benefits of the unregulated flow frequency curve to create your regulated one. So looking at this graph below, we can take your regulated flow frequency curve, and then we can pass it to this unregulated to regulated flow transform relationship to then get your regulated curve. So what's cool about this is the information that you got from your unregulated curve, right, that you spent time computing and generating, is passed down to your regulated curve. That's really cool. The challenge, of course, is how do you create this unregulated to regulated transform relationship? So there could be an existing function out there from like a water control manual or a previous analysis. But in most cases, you'll need to do some modeling, either a reservoir modeling or a hydraulic modeling to estimate what this regulated to unregulated relationship is. And then once you have the relationship, you can add this to FDA. So you can incorporate your unregulated flow frequency curve in your Monte Carlo analysis. Right. So this slide here, unregulated to regulated curves in action. So this is just kind of putting everything together. So let's say we have your unregulated frequency curve and your regulated frequency curve. So this will show you just how your frequency curve, right, which is one of the first inputs that you put into FDA, can impact your damage frequency curve, which is what you end up using to estimate your expected annual damages. Let's say you have a project where you're expanding the floodplain to allow more water to store over bank, and you want to see how expanding the floodplain helps with reducing your flood damages. Okay, so this project could be like a levee setback or maybe a levee removal, but the idea is just you have water that now goes over bank and you can store that. So for this example to kind of make more sense, we're going to interchange some terms here. This black line, which I've been using to say is unregulated, we're going to call this the without project. And then this dashed red line, which I've been calling regulated, we're going to call this the with project condition. So the with project is incorporating your levee setback or your levee removal. And so what this curve is saying is, this dashed red line, if you incorporate this project for this range of probabilities, this is going to be the peak flow discharge. Right, so this is as opposed to if you didn't have your project, right, you're going to have higher flows, right, because you don't have any of those flows being stored. Right, so going through this diagram in the without project condition. So in this first case, we have for a given probability the flow value for the without project condition. If we were to move down to your damage probability curve, this would be the expected damage that you might get. In the with project condition, shown here with this red dot, so we're not going to go to the black line, we're going to go to this red line. Right? And so this is going to be the expected flow for your with projects peak flow curve. And moving down the line, we can see that in this kind of example, we have no damages. Right, so this is just showcasing kind of the flood risk benefits of increasing by adding the with project and expanding your floodplain, what you might expect. And so this again also just kind of shows you how your inflow frequency, the first things that you put into your FDA, how that can impact your results. All right, so let's kind of move on to our last topic here with stage frequency. So stage frequencies can be used in lieu of flow frequency. And so the graph to your right here is an example of a flow frequency of a stage frequency. We know it's stage because on the y-axis it says stage. I have just a kind of a quiz question here for the group here. What do you think this graph is? Do you think it's an analytical curve or a graphical curve? If you guys think if it's an analytical curve, in your icons, why don't you use the rabbit icon if you think it's an analytical. If you think it's a graphical curve, use the tortoise icon. So I'll give you guys just a few seconds here, but if you think this is an analytical curve, use the rabbit icon. If you think it's a graphical curve, why don't you use the tortoise icon? So I'll just give you guys a few seconds to see what you guys think how this curve was generated. Very good. I see a lot of tortoises, and that is the case. So this was a graphical frequency curve. And the hint here would be there is no statistics that are shown on this plot, right? So we didn't use any statistics to generate this. And so this falls into the other category of it being a graphical frequency curve. All right, so going back to this image here, the stage frequency curve will take the place of the flow probability and flow stage relationship in FDA. So when do we use a stage frequency curve? So in general, again, we like unregulated flow frequency curves, but then there are times where we need to go straight to a stage frequency. There are two reasons that we have listed here. The first is when the stage to flow relationship is not one-to-one. And we'll go into a little more detail what that means. The second is if the data we have is stage data. So hopefully that's a little more intuitive, right? If you only have stage data available, then go with what information you have and use that. So going back to when a stage to flow is not one-to-one, the conditions for when that happens is when we have backwater. So backwater is when we have river stages downstream that impede incoming flow from upstream. So backwater can be caused by some downstream structure like a bridge or changes to channel geometry, where you can have a wide channel geometry, then a very narrow one suddenly. That can cause backwater. Tidal conditions and ice jams, those are other types of conditions that can cause backwater too. And because of these effects downstream, they end up creating changes to your flood stage relationship so that your flow and stage is not one-to-one. Right, and that information is important for FDA. The image that I'm showing to the right here is here in California. It's the confluence to the American and Sacramento River. The American River here is in the darker color on the right side, and then the Sacramento River is the lighter color on the left. Sacramento River, it's a much larger system, so the flows will tend to dominate here at the confluence. And so as flood magnitudes increase along the Sacramento, you can have flows along the American River that slow down or even go backwards as the stages along the Sacramento River start to increase. So then we end up losing that one-to-one relationship. And if you didn't know, Sacramento, the Sacramento River can also get affected by tides since the river flows out into the ocean. And so the tides can actually end up affecting the Sacramento River stages. And so the stages at Sacramento River also is not a one-to-one relationship. So going kind of back to this image, this kind of shows that problem of kind of not having something one-to-one. So for a given flow on your frequency curve, you can end up with two possible stages for a given flow, right? And so this ends up messing up your damage, the damage stage to damage probability curve. And then with the stage frequency curve here, this will take the place of your flow probability and flow stage relationship in FDA. So you still need to develop your stage frequency curve that incorporates the various scenarios to account for backwater. So your engineers should be modeling various scenarios with backwater to come up with this stage probability graph. All right, so at this point here, I'm going to pass it off to Brennan, and Brennan is going to talk about hydraulics and how the hydraulic information is used in FDA.
Yeah, thanks, David. Can everybody hear me first? And everybody, are you looking at my screen? All right. Cool. So I'm gonna get started. I'm gonna talk about the hydraulics portion of this lecture. I've got 4 goals that I really want to get through as part of this lecture. First thing we're going to talk about is what are hydraulics. So David's just talked a lot about hydrology. You know, the first H of H&H, I want to talk about the second H. What are hydraulics as opposed to hydrology? They are highly intermingled professions, disciplines, interests, but there's just kind of slight caveats. Then I want to talk about how hydraulics are used in FDA. So I want to point out, kind of as David did, which relationships belong to hydraulics, what inputs you put in, will you be getting from a hydraulic engineer, that kind of thing. My third point here, I'll be brief on, but I want to give all of you economists a little vocabulary crash course. Because economists, as the integrators in FDA, you're kind of expected to know a little bit about engineering, which is not super fair because engineers really don't have to know much about economics, but you guys have this extra burden, and I want to help you out with at least introducing you to some words that engineers are going to throw around at you and assume you know. Finally, I'm not a geotechnical engineer. I'm not going to talk about how to develop fragility curves, but I mean, I'm going to talk about how they're used as an input to FDA and how FDA is going to handle those. So starting with hydraulics as opposed to hydrology, most of what David just talked about was hydrology. It was coming up with flow relationships. The key there being that hydrology is about figuring out how much water is going to be in the stream. That's the whole deal. Hydraulics is, given some amount of water in the stream, how high is that water going to get? That's the simplest explanation of it. Hydraulics figures out how high the water is going to get, whereas hydrology figures out how much. And the way we're going to end up describing how high the water gets in FDA is through the use of a rating curve, and then through the input that is our hydraulic profiles, our water surface profiles, more specifically. So starting with that rating curve. Rating curves are provided to us by the USGS. They do a fabulous job of setting up gauges all over the United States on different streams, and they record stream data. For each one of these gauges, they also do a study to get measured flow data. And so with that, they can measure, they have a measured stage, they have a measured flow. They develop these relationships based on observed data of how water in this river flows. So for this gauge here, I've got at 20,000 CFS. The stage is something like 2,098 feet. That's the on this chart. That's the blue line. It would be USGS's observed data. Now, when I go and build a hydraulic model, because I want to know about the river all throughout it, not just at this point, I can use this as a calibration point or a validation point. I can look back and see, okay, USGS has measured the data. We know reality is that for this flow, the stage should be this, and for this flow, the stage should be this. Does my model reproduce that result? And in this case, I chose a project of mine where I did a very good job at my model. So it does match pretty dang good. Once I'm comfortable that my model is representing reality well, then I can go ahead and pull this relationship anywhere from my model. Anywhere in the stream. That anywhere is going to be called the index point. And we'll talk about that in later slides. But the rating curve is really just the relationship between flow and stage at some point in the channel. That rating curve is the flow stage relationship, which is the top left quadrant of our 4-chart FDA classic representation. Now, the other big hydraulic input, so we talked about rating curve, is the water surface profile. So this is can come in the form of depth grids or water surface elevation grids, more accurately. It can also be extracted straight from RAS results in FDA 2.0, but it is a list of inundation profiles for different events, is really all it ends up being. And the point of these is to be a relationship between our rating curve and the actual depth of water at structures. So in my image here, there's a big point with a star on it with the rating curve kind of called out. That's my index point. So I'm going to use that as my stage flow relationship in FDA. That's going to, whatever flow I sample off the analytical, or the flow frequency curve, I will translate that flow into a stage through that rating curve. But even though the water surface elevation at this point I've called out on the rating curve is 938 feet, that doesn't mean that when I go to calculate damages at every structure in my impact area, that the water surface is 938 feet. It's just not. And this water surface profile allows me to make that conversion. So what this is saying is when the rating curve is at 938 feet, I've extracted data from all of these structure points that say, okay, this structure is actually 932 feet when this is 938. And this one's 933. And so I can when I go to calculate damage at the structure, I have a relationship between the kind of aggregated representation of that rating curve and the actual depth at each of those individual structures. So to summarize that idea, David came up with stream flow. So we get some kind of a stream flow, and through the rating curve, we are going to translate that into a stage. So flow becomes a stage. But we don't want to use that stage to calculate the damage at every structure. So we're going to use the water surface profile to translate that channel stage into a stage at a structure. And we will use that to calculate the damage at that structure for our next relationship. So that kind of completes my explanation of what hydraulics are doing in FDA. Now I'm moving on to some terminology. And I'm going to be pretty brief here, keeping an eye on the time. But I've decided these 4 words are important because they come up in scoping projects and when hydraulic modelers are talking big picture about what the model needs to be and making kind of the big overarching modeling decisions. Those are steady versus unsteady flow and 1D versus 2D modeling. So both of these are just ways of approaching hydraulic problems in building models. Steady state hydraulics are the simplest version of hydraulics. To answer the question, what would our system look like if the flow was X? So essentially we take this river, we draw a bunch of lines through it and we say, okay, the flow everywhere in this river is this value. How high is the water going to be? What I want you to latch on about this is this has no sense of timing. We're not like simulating a river rising and falling. We are just taking individual flatline hydrographs that we assume have always been and will always be. The time here is just infinite, and we are setting the flow in this river. This is especially tricky when there is storage in the overbanks of a river that's significant. So if a levee overtops, if in a steady state model, we have no way of like knowing how much that area is going to fill up. We can't like calculate how long it's going to be overtopping and calculate some volume from that. We have no sense of time. So this is typically why steady state would get thrown out. It's very tricky that way. My animation here is just me clicking through these different hydrographs. So I've mapped Muncie, Indiana with a steady state model, clicking through those hydrographs. The counter to steady state model is the unsteady state, which should be much more intuitive, I hope. In this one, we actually simulate a river rising and falling. We have some kind of event that we are simulating through our model. It's great. You can see I'm simulating the same area as I was in the last, but in this one, you're seeing water actually pour over that levee and kind of move through the system. Whereas if I jump back, as this guy clicks through, water is just kind of like jumping places. This is a much coarser approximation of the solution. This is a lot more detailed way of modeling something. This is especially important when you have leveed areas that are going to potentially fill up with water. Another kind of technical detail here, a logistical interesting thing. When you're handed steady state hydraulics, all of these profiles out of RAS typically come in one HDF file. When you do unsteady hydraulics, you'll get one for each event. So just to point out that I try to give you some introduction to that so it's not confusing when that happens to you. It does change the output format from RAS to use a different type of modeling here. So steady versus unsteady, what I want you to take away from that is that unsteady state modeling has a sense of timing, and it's important when there's storage outside of the channel, when there might be a levee or some really large overbank that might take volume away from the channel. That's when timing becomes important to modeling, and steady might not be appropriate, even though steady is the easier way to model, oftentimes. So moving on to 1D hydraulics. 1D stands for one dimension. Typically, I usually think of it as water moving in one direction. Water is just going downstream. It's a super efficient way to model. They can be unsteady or steady models. We're looking at Muncie, Indiana. In my picture here, the flow is going down. The little area outlined in kind of a periwinkle shaded thing, that is marking off a levied area. So that's an overbank. And then, of course, the river has these green lines through it. Those green lines are cross sections. Cross sections are the primary component of a one-dimensional model. We make a couple assertions about cross sections. The big one is that water surface is flat across that line, and that water is always going to flow perpendicular to that line. This is really easy when water stays mostly in a channel. If you look at the very top of my picture here, that top right-hand corner, I'm only using cross sections to model this area because water, I'm saying, is staying in that channel. I don't need to consider what's going on in that overbank because water is not getting out of the channel. It's very easy to say that the water surface across the channel is flat and it is moving downstream. This gets trickier when we have a levee though, because now when I go down past this kind of first bridge that you see in my model and that periwinkle area starts, periwinkle might not be the right name of that color. I just realized that. I've never had that confirmed for me. But you see that now I'm using a cross section and that kind of outline because once water breaches over that levee, there's no way for me to draw a line that obeys the assertions of the cross section. Because as water's spilling over that levee, it's going to start going a different direction than the water in the channel, and it's going to be at a different elevation. You know, it's not going to instantly fill up to the height of the channel. There's some storage going on there. The one-dimensional way to handle that is to use a storage area. Now, storage areas are just big bathtubs. They fill with water from the lowest point, and we calculate how long water is spilling over to get a volume to put in our bathtub. This is the best we had for a while, so it's what we did. It can be kind of tricky because, as you see over here, there's a lot of water in that storage area towards the bottom. That's because that's the lowest point. But all the water is actually spilling out at the top, kind of up where I have the flow direction arrow. The levee is actually breached up here, and water is flowing across this whole thing in reality, but my model's not capturing that. There's a whole bunch of damages I'm just flat missing because I made too heavy an assumption with my 1D hydraulic model here. A better way to approach that kind of a problem and how I approached this problem, we're looking at Glendive, Montana. Here, I'm using 2D hydraulics. 2D hydraulics is the cooler, newer, more shiny way to answer these questions. We lay out a grid over our study area, and we allow water to flow from grid cell to grid cell on a two-dimensional plane. That's where the 2D comes from. This can capture lots of different flow directions. So in Glendive,